this set of Snap Circuits videos, we're now looking at the SC750 set, with projects going from 512 to 692, including the additional projects that make use of the computer interface cable, which we'll look at when we get to that point. So with this set, we get introduced to our solar panel, our electromagnet with its iron core rod, the vibration switch, the bag of paper clips, which we're going to use with the electromagnet, and then we also have our 2-spring socket for any custom components that we want to test in a circuit. Diagnostics and stuff, just the projects. Now, I do have a bit of a complaint that I have with this, because I'm looking at some of these projects, and you can probably understand where I'm coming from when you look at some of these. But these are projects that I'm seeing from the first couple of pages here that could have easily been done with the SC500 system and not need a whole nother system like the SC750 to do. You'd have to buy the upgrade kit to the SC750 if you had a 500 to do these additional projects, just because they're in the manual here. That's just my one little graph I have there. But anyway, let's get started with the projects. So we're going to start with Project 512 here, which is the Siren. And there it is in the book. And here it is on the board, as usual. Plug it into power. So here we've got, again, another resonating circuit, making use of our NPN and PNP transistors together to create a waveform, and then it's being fed to our transformer, which outputs to our speaker, making use of our C1 and C3 capacitors. The C3 capacitor is actually being used for the frequency and duration of the oscillation of the circuit, along with a couple of our resistors to help control it. So when we turn it on, not a whole lot is going on right now, because C3, our capacitor there, is discharged, but we need to charge it up so that we can produce a tone. So when I press the press switch in, you hear the siren kind of come up really quick and then go away. Now, it is putting audio out when it's up that high, it's just that it's such a high frequency that we can't hear it. Now if we turn the circuit off and back on, that allows it to discharge. So we kind of need to press down the press switch and hold it up to a certain point and then let it go, because it will charge up the capacitor, increasing the frequency, and then as that capacitor discharges after we release the button, the frequency decreases till it kind of just makes a ticking noise. So I went a little too far there. You can hear the frequency of it going down as the capacitor discharges, but as we charge it up, the frequency goes up. Now, that's essentially how Project 512 works. Now, an interesting thing I discovered that the book doesn't mention is you can also play around with this circuit just using your hands and your own resistance of the human body to control the rate that this capacitor both charges up, increasing the frequency, but also control how fast it's discharging, decreasing the frequency. So let me turn it back on. So this, what we're going to do is basically bypass the press switch. So by putting one finger on the base of the PNP here, and then we'll go to something like the negative rail here, since the PNP likes to reference to ground. As I put it on the ground here, you can hear the capacitor charging up because the frequency of the circuit is going up. Now, if I take my other finger and put it on the positive 6-volt rail, it will actually decrease in frequency faster than what it is right now. So by using your hands, you can also manipulate the circuit by keeping one finger on the base of the PNP there, and then changing between using ground and positive voltage to control the frequency of the circuit by how much that transistor turns on to charge that capacitor there. So anyway, that's 512, so we're going to move on to Project 513, which is the electronic rain. So here we are with Project 513, electronic rain. There it is in the book, and here it is on the board. So again, we get another oscillating circuit, strictly just using our NPN transistor this time, coupled with a 100 microfarad capacitor and the 10 microfarad capacitor. And then of course it's being outputted to our transformer going through our speaker. But this time we have some adjustability because we have our variable resistor here that can control the frequency of the circuit, how many times it oscillates. So we turn it on here. The speaker is kind of making a chirp at about that rate. And if we turn it to the left, the circuit slows down. It oscillates slower. And of course, if we go the other way, changing the resistance, now it oscillates faster. And again, I don't know how much the camera is picking it up from the distance there. Bring it down. All the way down. And if you want to change the rate of the oscillation, you can go to a lower resistor on there, like resistor 3 that's 5.1K, or even R2 that's only 1K, and that will make the oscillation speed up a lot more. But that's essentially how Project 513 works. So now we're going to move on to Project 514, that they call the Leaky Faucet. So here we are with Project 514, the Leaky Faucet. There it is in the book, and here it is on the board. So again, another oscillator circuit, making use of our NPN transistor and 100 microfarad capacitor. And we're using our variable resistor to control the oscillation. And it's going to our transformer, along with our 5.1K resistor, but our output is coming through a whistle chip and not the speaker. And you notice we're not using the output ends here, the transformer, so we're not stepping down, we're actually just using the transformer here to help the whistle chip work. So we turn on the circuit with the variable resistor all the way to the right there. You kind of hear a ticking sound from the whistle chip, which of course they're trying to make sounds like a leaky faucet. And of course, if we move the variable resistor to the left, the oscillation speeds up. In which case we can go all the way to the left. So that's how Project 514 works. And now we're going to look at Project 515, which is the lamp and fan independent. So here we have Project 515, So here we are with Project 515, the lamp and fan independent. And there it is in the book, and here it is on the board. Now, as I said earlier in this video, my thing about projects that could have been done in earlier sets, this is very clearly a project that a person can do with the SC100. It's a 2.5 volt lamp, the motor, press switch, slide switch, a few connections, and a 3 volt battery box. Yet it's all the way here in the project manual for the SC750 now. I'm not sure if I can really fault them for it, because if you look at the manual here, it says This circuit was suggested by Luke S. of Westboro, Massachusetts. So there are suggested circuits included in this manual from Snap Circuits users that got implemented into the manual here. I don't know if I ever mentioned it or not, but there is a Snap Circuits builder on the Snap Circuits website. So if you design your own circuit with your Snap Circuit system, you can go to their builder online on the site, redesign it in that Snap Circuits builder, and basically be able to publish it to them. And they'll either display it on their site and maybe even put it in a future manual for a future Snap Circuit system, who knows. But that's how they got that in there. But again, as I say, it's just one of those things that you could easily do with the SC100 that didn't need to be in an SC750 manual. So anyway, obviously the circuit is pretty simple. We have, again, our 3-volt battery box, 2.5-volt lamp, and our DC motor with the fan attached. And they run independently, so when we turn our slide switch on, hey, they completes the circuit for the 2.5-volt lamp. The 2.5-volt lamp lights up. Press the press switch. Our motor comes on, our fan spins, and we let the press switch go. Obviously the fan stops. And of course we can run them together. So that's really all there is for Project 515. So now we're going to move on to Project 516, which is Drawing Resistors. So here we are with Project 516, Drawing Resistors. There it is in the book, and there it is assembled on the board. So we've got our simple oscillator circuit here, running at 6 volts through our NPN transistor, with our 1K and 100K resistors there, along with our C1 capacitor feeding our transformer and then outputting to our speaker. And we got a pair of jumper wires hooked up because we're going to be testing various different sets here to control basically the oscillation rate and the output sound. So push this out of the way for the moment, because in the book here it has this basically what they call drawing resistors. So we take a number 2 pencil and we fill in these boxes, which you see I've already done here, and they're at varying sizes and lengths. And because of that, while each one is a different size and different length, they're supposedly about the same resistance according to the book. So I'm going to have the circuit up here, so it's going to be slightly out of frame. I'll try to see what's going on. Now when the circuit's powered on, obviously nothing's going to happen because the circuit's not oscillating. If we bring these together, you can hear that the circuit works and it oscillates at a fairly high frequency. Now because I have to take the jumper wires and put them across these, to keep myself from actually becoming part of the circuit itself, I'm going to isolate myself by doing these with a pair of gloves, because gloves help act as an insulator. So this way, while I'm holding the jumper wires, it's not taking me into account to control the oscillation of the circuit. So if I hold these, see, I'm insulated, so it's not using my skin to control it. So let's try to go on the first resistor here, see if we can get some oscillation to occur without these physically touching each other. It's going to take a little while. So you can hear the circuit oscillating there, producing a frequency. And again, I'm trying to hold it on here. And so what's happening is that our oscillating signal is going through one wire here, and it's going through the graphite that we've created on the page here, and then coming back on the other wire, and that's making the circuit oscillate. And because the graphite is acting like a resistor, it oscillates at a different frequency than if it was just a direct short like that. So let's go down to the next one. And of course you can move these back and forth to change the oscillation. Let's go to the third one. Now, even though they're supposed to be roughly the same according to the book, you can hear the differences on them, and also how much the distance between the jumper wires affects how much the circuit oscillates. So let's go to the last one. So that's essentially how Project 516 works, using these different sets of filled-in graphite from a number 2 pencil to create different varying resistors. So I'm going to move on to Project 517, and they call this the Electronic Kazoo. And basically it's working on the same principle as before. We just have one long continuous line, which you see that the amount of graphite we have here varies from very wide to becoming very narrow to just a line here. So what we can do is take our jumper wire and keep it pressed at the end here, and then we use our other one and run it along here. And as the resistance changes, of course, the oscillations or frequency of the output of the circuit will change as well. So we'll start close together, and then I'll try to move it away. And you see, as we get more and more resistance, the circuit gets to a point where it's oscillating slower and slower, to where now it's just ticking. And we can come all the way to the end here. And you notice when I come off the trace that I made, it stops ticking because there's so much resistance on the paper that it can't make the circuit oscillate, so we need to use the graphite that we made to get the circuit to oscillate. Just trying to keep it on the line here. Okay, resistance is decreasing. Oscillations are getting faster and faster. So again, that's the same principle as the last project, but this time we have one long continuous line here of varying size that allows us to change the resistance as we go along. So now we're going to go to Project 518. Move this up a little bit. So we got the Electronic Kazoo 2, and this time we have dots that we fill in, but we still use a line that gradually decreases in size the further to the right that we go. So we'll try it again here. Put this on the number 1 spot and hold it there. We'll take my other jumper lead and we'll run it along here. Let's see how that sounds. So I've got it on the number 2 spot. There's number 3, number 4, number 5, number 6. And as you can tell, the further away we get from number 1 here, as this line gets smaller and smaller, the more resistance there is and the less oscillations the circuit makes, so the frequency is lower. So number 7, number 8, getting slower, number 9, if I can get a connection here. Seems I have. a break in my connection there. Fix that real quick. See if I can fix my connections. Which one is? Not that it's going to be a very good fix. Let's see if we got it there. Yeah, there we go. Number 10. Oh, got a broken connection again. And here's 10. And 11. It might be because this scrap is drying up just a little bit. Oh, that's good. My connections come off there. And there's 11. Go back up. And it starts getting faster. So that's basically the idea of the Electronic Kazoo 2 Project 518. So we're going to look at the last project using this oscillator circuit, which is 519 and the Water Resistor. And for that, it's a lot simpler. Set it back in. And I got my cup of water here in this Welch's Tom and Jerry cup from long ago. So we'll just stick our jumper wires in there, and then we'll use the water itself as resistance to make the circuit oscillate. So you see it's oscillating at a much higher frequency than when we were using the graphite on the paper there, because there's even less resistance in the water here than what was done on the paper there using the graphite and number 2 pencils. And again, depending how far this is in the water, we can change that resistance. And I can do that with the other one too. And that's basically how that works with Project 519 using water. And of course you can do varying other things too, like add salt to the water to make it a brine so that it decreases the resistance even more and makes the circuit oscillate even faster. But that's pretty much it for Project 519, so now we're going to move on to Project 520, which is a 2-transistor oscillator. So here we are with Project 520, the 2-transistor oscillator. There it is in the book, and here it is on the board. Now we've actually used 2-transistor oscillators before. So we've got our PNP transistor and our NPN transistor. We've got our variable resistor here that helps control the oscillation in the circuit. Our transformer with our speaker on the output there, so that's where we're going to hear the oscillations from. And of course we got a couple of resistors and a couple of capacitors to help with the control and operation of the circuit's oscillation. So we turn on the slide switch and nothing happens. Now the funny thing is, and some of you guys probably know already by looking at how the circuit is wired, the PNP transistor here has nothing to do with the oscillation of the circuit here. All it's doing with the press switch here is turning the PNP transistor on and off so that it supplies power to the rest of the circuit. Otherwise I could just connect a wire from the slide switch here to here and it would still work normally. So the PNP is doing nothing here than acting like a switch, which we turn on and off with the press switch. So when I hold the press switch down, our circuit begins oscillating through the NPN transistor there, and then we hear it through our speaker on the transformer. And by adjusting the resistance on our variable resistor here, we can control the rate of oscillation. So that's how project number 520 works. Again, as I say, it's a little silly that the PNP is being kind of used as a redundant switch there, but that's how they designed it. So now we're going to move on to project 521, which is Diode. So here we are at project 521, Diode. There it is in the book, and here it is on the board. So it's a relatively simple circuit. We have a 6-volt supply with our slide switch controlling power to the whole circuit. We have our D3 diode coming out, and then we have our 6-volt lamp before the diode, and then after the diode we have our red LED being limited by our 5.1K resistor, and we also have a 470 microfarad capacitor in parallel with it. So when we turn on the slide switch, our 6-volt lamp lights up nice and bright, and our LED comes on because it's also getting power through our diode. Now when we turn the switch off, the 6-volt lamp goes out, but the LED stays lit and slowly gets dimmer and dimmer because it's being powered from the 470 microfarad capacitor discharging it in this loop. So what happens is when we have the slide switch on, power is going through our 6-volt lamp in this loop, but we also have a loop going through our diode there, but we also have one going through our 470 microfarad capacitor, so it's charging that capacitor up. And then when we turn the circuit off, well, now the capacitor discharges in a loop through our red LED there, but the D3 diode here does not allow the capacitor to discharge through the lamp here, because if it was, the LED there would immediately go out when the lamp does when we turn the circuit off, if this was just a 3 snap across here. But because the diode prevents current from going in the opposite direction, it only discharges through the LED. So that is how Project 521 works. So Project 522 is the rectifier. Okay, here we are with Project 522, the rectifier. There it is in the book, and here it is on the board. Now I've chosen to modify the circuit a little bit because it usually has the speaker here, but I've chosen to put the motor on it instead because the power amplifier, of course, amplifies power and makes it a lot louder through the speaker, and I kind of want the circuit a little quieter, so I replaced it with the motor so we can hear it through the motor instead, and we'll still get the same effect as before. Actually, we'll get a little bit of a better effect for what the circuit's trying to demonstrate. So we've got our 6-volt supply here, our slide switch that turns the power on and off to our amplifier IC, and we have our, again, motor on the output here, but it's also going through our R3 diode, our 470 microfarad capacitor, our red LED, which is being limited by resistor 2, 1000 ohms, and we have our variable resistor over here going through our 5.1 thousand ohm resistor and our 0.02 microfarad capacitor to help with oscillation. Because what's going to happen is the output from the power amplifier here will create an AC signal, an alternating current signal. But of course, we need direct current to run our LED, so that is what the D3 diode is for. So it will rectify the current on the peak coming out of the amplifier. But because there's a D3 diode here, our capacitor will get charged up on the peaks but will not discharge on the lower parts of the amplifier there, because again, remember, it's an alternating AC signal and we only want the peaks going in here so that our light lights up and keeps our capacitor charged. So we turn the circuit on. We have our variable resistor set to about the middle setting. You can hear our motor humming away here from the AC signal that's going into it from the power amplifier, and you see that our LED is on nice and bright. And again, we're hearing the motor whine because of the AC signal, but it's DC that's powering our LED here. Again, that's being rectified by our diode there, but it's also charging up our capacitor because the capacitor is helping to power the LED there. Because if we didn't have it, you see our LED there doesn't light up very well, so that's where our capacitor comes into play. So it essentially rectifies the alternating current coming out of the power amplifier. So that is Project 522. So now we're going to look at Project 523, the Motor Rectifier. So here we are at Project 523, the Motor Rectifier. There it is in the book, and here it is on the board. So here we've got our transformer, and it's producing an AC output that's being rectified by our D3 diode here. And then it's flowing through our meter on the low current setting through our 10,000 ohm resistor, and we do have our C2 capacitor here to provide a little bit of noise filtering on that. And then on the input side of our transformer, of course we got 3 volts going in, we have our motor, and then we have a press switch that connects a 470 microfarad capacitor in parallel with that motor, and then of course our slide switch that turns the circuit on and off. So when we turn on the slide switch, our motor spins up, and you see that we've got current showing on our meter there. Now what's happening is as the motor is turning, it's quickly connecting and disconnecting there inside there, creating a pulsed DC on here, which is the transformer wants, and that's creating an AC output, but we need DC to measure it on the meter. So that's why it gets rectified, or I should say half-wave rectified by our D3 diode here, giving us a current measurement. Now if we connect the capacitor in line with the motor, you see our current pretty much goes all the way to 0 on the meter there. And that's because when we put the capacitor in line with the motor, we cancel out the AC ripple noise that the motor is making. Therefore the transformer doesn't really have any on and off input on it to generate an AC signal on the output there that our meter will see. But once I take the capacitor out of it, now we got the AC ripple back, so now our transformer is producing an output. And again, it's being rectified by our D3 diode there. So that's Project 523. So now we're going to look at the last Project 524, the SCR Shutdown. So here we are with Project 524, the SCR Shutdown. There it is in the book, and here it is on the board. So in this circuit, we have our NPN transistor that's switching on and off, controlling the current to our red LED there. And that NPN transistor is being controlled through our variable resistor through our SCR. So when the SCR powers up, it then powers on our NPN transistor, allowing our red LED to come on. Now depending on where our variable resistor is set, that determines if there's enough load on the SCR for the SCR to stay on once we activate it. If the current is too low, the SCR won't stay on when we release the press switch. If it's high enough, then the SCR will stay on, keeping our NPN transistor on, thus keeping our red LED on. So we turn the circuit on. Obviously nothing happens because the SCR has not been set to turn on. So we press our press switch, the SCR turns on, and because our variable resistor is set all the way up, there's enough of a current drain on it that it keeps the SCR turned on, thus our NPN transistor stays on and our red LED stays lit up. Now, if we bring our variable resistor down some, say just above the middle there, and we try this again, we press the press switch, we can turn the SCR on and turn our LED on, but when we release it, it can still stay on because there's just enough current there. So let's bring it down some more to about the midway point. Press press switch, release it, and now there's not enough current being drained on the SCR there in order for the SCR to remain in the on setting. So as soon as we release the pressure switch, it turns it back off. So let's push the rear resistor back up, press the pressure switch, and now there's again enough drain on the SCR there. Bring it down and it turns off. So that's how project number 524 works, and that concludes this set of Snap Circuits projects.